Okay, let's start, all right? So let's continue from last time, talk about regression. So we did some basic true if our n is really, really large. Right? In large sample, that this is the formula for the variance of beta hat. In small sample, if we are not in large sample, then this formula invariably has, it's not the, so we don't really have a formula for small sample or medium sample, okay? So we have, this is a formula for a large sample. Now, one thing that I didn't ask you last time is that the t-statistic, right? So this t-statistic, when we do hypothesis testing, we say, okay, this thing, right, this t-statistic goes to normal distribution 0, 1, again, in large sample, right? And if our H0 is beta j star equal to 0, then we are left with beta j hat divided by our estimated standard deviance, standard error of the beta hat, and then we have a normal 0, 1. The question is, why is it called a t-statistic? So do people remember why it's called a t-statistic? Because it follows t-distribution. But are we having t-distribution here? No, it's a normal distribution. So where's the t-distribution? Yes, when n is large, it goes to a normal distribution. But when n is small, so I said this is asymptotic, right? This is when n is really large. So when n is large, when we do not have large sample, is this one a t-distribution? Actually, no. It's not a t-distribution, okay? We do not know what distribution it is in finite if we do not have large sample. Now, the reason why it's called t-statistic is because we only know its distribution if we make very strong assumptions. Specifically, if we assume our model is y equal to beta x, okay, beta prime x plus e, right? So this is our linear regression model. We have not made any assumption on the e, okay, the distribution of e. But if we're going to put a very strong assumption, which is e is normal distribution, 0 sigma squared, okay? If we make this assumption that this distribution of E is normal, then this t-statistic is actually follows the t-distribution. So only when this assumption is satisfied do we have a t-distribution. And then we can do hypothesis testing, right? And we should be pretty sure that our hypothesis testing is very good even in very finite samples. Right. But if we're not willing to make this assumption, then we don't know anything about the distribution of t unless we are in large samples where we have this large sample approximation, okay? Asymptotic. So today we're going to begin with a discussion about another method that we can use to estimate standard error. Right? The method we talked about last time is basically we estimate this formula, right? So we estimate the variance beta, and we use it to do hypothesis testing, right? So we estimate the variance according to this formula. So today we're going to begin discussing another method we can use to estimate the standard error of beta hat, and that is Bootstrap. Okay. So the idea of bootstrapping, Bootstrap is a very, very general technique or idea. So, but in this lecture we're going to embed Bootstrap or introduce Bootstrap in the context of estimating the standard errors of our estimate. Now the idea, so let's first take a look at a very simple example. Okay, suppose we have two variables x and y. Right, you can imagine the x and y are just putting the story. X and y are returns of two financial assets. Right, so we'll go. Suppose we put them in a portfolio, and let me just assume that they have the same expected return, so that the goal of deciding how much money I want to put in the first asset and how much I want to put in the second asset essentially is minimizing the variance. Okay, so I want to find a gamma such that I minimize the variance of this portfolio. Right, the portfolio is gamma in x, 1 minus gamma in y, and of course if you solve this, the solution is pretty simple. It's sigma. It's the variance of y minus the covariance xy divided by variance x plus variance y. Basically we have this formula. So how do we calculate this alpha? suppose we do not know what sigma y is. I do not know what sigma x is, right? I know nothing about the variance and covariance. How do I calculate this alpha? This alpha is the optimal percentage of my portfolio that should be invested in X, right? For the X. Okay, so how do I do it? Well, I have to estimate it. So suppose there's underlying X and Y. So X and Y, and there's the underlying population of how these X, Y are, what their joint distribution look like. Now, so what I can do is I can try to get some sample, right? So from this underlying distribution, I can generate or I can draw some samples of data. Okay. So X and Y, this is one data set. And then based on this data set, I can calculate this alpha. Right. How do I calculate this alpha? Well, because based on this data set, I can calculate sigma square, sigma hat Y, right? The variance of Y, the variance of X, the covariance of XY, right? So I can calculate these values based on my data set, right? Okay, so and once using these numbers, I can calculate the alpha hat. Now the problem is, yes, I can do that, but I do not know how good my alpha hat is, in a sense that I do not know, for example, the variance, right? The standard error of my alpha hat. How do I figure out the standard error of my alpha hat? Or the variance, right? How do I figure out the variance of my estimated alpha hat? That's a question. Now, before we talk about Bootstrap, right? Let's imagine that we somehow can repeatedly draw from the underlying distribution. Suppose we have the ability to draw many times, infinite times, from the underlying distribution. Every time we can draw n data points, suppose, okay? Then a very easy way to figure out the variance of this alpha hat is I can just draw many times, right? I can draw many data sets. Okay? So just draw many data sets. Every time we end up having different data, and based on every data set, I can calculate alpha hat. Because every data set will give me a different variance of Y, variance of X, and covariance XY. So every data set will give me a different alpha hat. Right? So I end up with many different alpha hat. And the variance of alpha hat is basically the variance of all the different alpha hat from all these data sets. It's that easy, right? Should be very obvious. Okay. So as an example, let's see, I generate 100, right? N equal to 100. So every time I draw 100 data from the underlying distribution, so this is one data set, right? We have 4 data sets here. Based on each data set, I can calculate what this alpha is. So the alpha value is, 0.576, 0.532, etc., etc. And if I do this enough times, I can calculate the variance of my alpha hat. And I know how good my alpha hat is, right? Okay. So let me use alpha hat R to denote the alpha hat I can calculate using the rth data set. So my final estimate of alpha hat can just be the average of them, and the standard error is basically the variance, right, of all the square root of the variance of all the alpha hat for all these data sets. All right. Okay, so in our simulation here, every time I draw 100 data, and we do this 1,000 times, so one run, so we do the simulation one time, and then we end up with alpha hat equal to 0.599 and standard error equal to 0.083. The true value of alpha is 0.6, okay? So we end up with a pretty good estimate, and we know the variance of our estimate. This is the standard error. Now the problem with this approach is that, here's a histogram, right, of all the our alpha hat based on all the generated data. The problem with this approach is that you cannot really do this in reality, because in reality we do not have access to the underlying true distribution, right? So you cannot repeatedly draw from the underlying distribution. If you can, then of course it's easy to figure out the standard error of your estimate. So what can we do in reality? Well, in reality, we only have one data set. Okay? Most often, we only have one data set that is drawn from the underlying distribution. You cannot draw more, right? You cannot repeatedly draw from the underlying distribution. You only have one data set. And here is what Bootstrap comes in, right? So what the idea of Bootstrap is I still try to generate many data sets, okay? I still want to generate many data sets, but how do I do it? Well, I generate all the additional data set from the only data set I have. The idea is this data set, that's the only data set I have. But if the distribution, in this data set, we can also have distribution of different values of x, right? Or x, y. So in this data set, if this data set resembles the underlying population, that's the idea. The idea is if this resembles the underlying population, then instead of draw from the underlying distribution, I can just draw from this data set. Okay? The simple idea is basically this, that we're going to repeatedly draw from the only data set we have. And in order to generate more and more data set. And then I can calculate my alpha on each data, and then look at their variance. I average them and look at their variance, and they give me an estimate of the variance of alpha hat. Okay? But how do I draw new data set from the old data set? How do I do it? Well, so, oh, there we go. So suppose I have n data. Let's just say, let's look at a single data set, which I have only one variable x. Suppose x has only, suppose x has only two values, okay? X either 1 or 0. And let's say I have 5 data points. Okay? That's my only data set. And this data set is drawn from the underlying distribution. The underlying population has many different x, right? Numerous x. Now, I'm going to say, okay, my only data set is 1, 1, 1, 0, 0. Now, what this data set tells me, if we believe that this data set exactly reflects the underlying population frequency. So here, x equal to 1 with, what probability? 60% probability, right? X equal to 0 with 40% probability. Okay, in my data set. Now, if I assume that this is exactly the frequency in the underlying distribution, then I'm just, instead of drawing from the underlying distribution, I'm just going to draw from my data set. And how do I draw it? I'm going to generate many new data sets. And each data set also has 5 data points. Okay? When we do Bootstrap, typically we generate new data sets that are of the same size as the original data set. So we're going to generate many new data sets. Each one has 5 data points. So how do we do it? You say, can I just, if I draw one of them from this data set, then I'm only left with 4 points. The second time I can maybe draw 0. I'm only left with 3 points. Then if I draw 5 points, I will end up exactly the same as before, right? So in this case, I cannot really generate new data sets, which means I cannot do this. The method I just described is called draw without replacement. By without replacement, we mean once I draw this data set, okay, once I draw this number into my data set, this is gone. The second time I'm going to draw a new number, I'm going to draw 0, then the 0 is gone. And the third time I'm going to draw 0, then this is gone. So you will end up with exactly the same data as before. That's called without replacement. But Bootstrap doesn't do this way, okay? When we do Bootstrap, we draw with replacement. By with replacement, I mean every time I draw something, so for example, I draw a number 1 from this data set. So this is the number 1 I draw. Okay? After I draw this one into my new data set, I'm going to, with replacement, means I'm going to replace it. Okay? I'm going to put it back into the original data set. And then I'm going to draw it again. And so the second time, maybe I draw a 0. So maybe this one 0. And then I'm going to replace the 0. I'm going to put it back. So basically, every time I'm drawing from exactly the same data. and I draw this 5 times. And this will often give you a different data set than the original one, right? It's very possible that if I draw 5 data points from this, it's very possible that I end up with 1, 0, 0, 0, 1, 1, right? Sorry. Okay. It's very possible that I end up with something like this, with 3, 0, and 2, 1, or even 4, 0, and 1, 1, or maybe, all 5 ones, it could happen too. Because every time I'm drawing from this same data set, basically give me a 60% of 1 and a 40% of 0. So I can end up with all kinds of new data sets. Right? Now the idea here is that when we are generating all these new data sets, every data point in this new data set is drawn from the same underlying distribution, okay, which is this. So in the end, I have a bunch of data sets that follows from this distribution, okay, drawn from distribution. And I can treat these new data sets as if they are drawn from the underlying distribution. And then I can calculate my alpha hat here, my alpha hat here, my alpha hat here, and their variance should give me an estimate of the true variance of my alpha hat. Okay. So let's take a look. This is exactly, I'll talk about the coding later, right? But here is what happens when we do this Bootstrap procedure. Okay, I hope now everybody has an idea. The basic gist, okay, the way that Bootstrap is done is that we only have one data set, but I'm going to treat this data set as if it's the underlying population, and I'm going to draw repeatedly from it to generate many new data sets. And when I draw this, I am drawing with replacement. So every data point is drawn from the same distribution, and I use it to generate many new ones. On each new data set, I'm going to calculate the alpha, right? The alpha hat. And then I can look at the distribution of the alpha hat. Okay? So this is the distribution of the alpha hat from our Bootstrap, okay, by doing this Bootstrap thing. So what I'm doing here is I'm doing 1,000 Bootstrap, meaning I draw 1,000 new data sets from my only data set, all right? And I calculate the alpha hat on each one, so that gave me this kind of distribution. Compared with the original, this is the true distribution of alpha hat. So this is the distribution of alpha hat if we generate new data sets from the true distribution. This is the distribution of our hat if we draw new data sets from my data set, observed data set, rather from the true distribution. So you can see they're actually, they're different, and there's going to be some bias here, but it's pretty close in our case. Okay. If we take a look at the coding here, right? So given any data, the portfolio data is the return of two assets, X and Y. That's the portfolio data. What I'm going to do is I'm going to generate one new data set using sample command. Right? Sample n means from a data set of n data points, I'm going to generate a new data set of n points by sampling with replacement. Okay, with replacement equal to true. So that's give me a new data set, and I can calculate alpha on this new data set. So this is one new data set. Now, if we do this 1,000 times, okay, in R you can just use a boot command. I'm not going to write a code for the for loop for 1,000 times. I'm just going to use a command program written by somebody else. But the idea is I draw repeatedly for 1,000 times from my data set. And then I'm going to calculate alpha on each one. And this is the result, right? For the 1,000 different alpha hats, the standard error is 0.087. That's the standard error of my alpha hat from this 1,000 Bootstrap samples. And that gives us a pretty good estimate of the standard error of alpha. Okay. All right, you can try yourself, but now let's take a look at one more example. So this is an example of the automobile. Yeah, question.
My question. This method, Bootstrap,
Mm-hmm.
it will definitely have a bias.
Yes, well, it depends on the bias. Yes, you'll have bias in the sense that I'm drawing not from the true underlying distribution. I'm drawing from my only data set, right? So how much bias it has depends on what? Depends on how much your data set resembles the underlying distribution. So, which means if you are bootstrapping from a very small data set, the n is very small, like 5 data points here, you're going to have some very bad results. But if your data set is very large, okay, 10,000, 100,000, you have lots of data, then you can pretty sure that your data set is already pretty much closely resemble the underlying distribution. Then if you do bootstrapping in that case, you end up with a very good estimate. So that's it. So that's a good question, which brings me back to the formula before. Remember, I said that if we do this, okay, if we use this formula to calculate the variance of beta hat, one problem is this is only asymptotic, meaning that this formula is only correct if we're in large sample, if our n is really, really large. Okay. Now, for Bootstrap, we don't have to have asymptotic. The standard error estimated by Bootstrap applies to finite sample, right, of medium size as well. It's not only we don't really have to have n really, really large. However, for Bootstrap, you also cannot have n very small, just like I said, because when n is small, your data set is a pretty bad resemblance to the underlying distribution. So for Bootstrap, it's also the case that when n is large, you get better estimate of a standard error. When n is small, you don't get very good. So so there's no escaping from the fact that when your n is small, we don't have very good estimate of a standard error. There's no escaping from that. But as we see in many cases, that Bootstrap provides us with a better estimate of standard error than using asymptotic formula. Indeed, the example I'm going to show you is one case like that. So let's go back to the automobile example. Now, this is miles per gallon on a y variable. So this is the data set has been used numerous times on automobiles. What is the relation between horsepower, for example, and how many miles per gallon this automobile can drive? As you can see that here we are fitting three we're fitting three functions on the fitting three lines on the data. This is the linear model, right? This is a polynomial model. These two are polynomial. Let's focus on the linear model. The linear model is this yellow line. Okay. Now, first question is, do you think the linear model gives a good fit? Well, that's a question that we actually will discuss later, but let's suppose we do this linear model. Let's look at the error term, okay? So this is the error. Here the error is here. Now here the error is, goes around. You can see that for this part of the model, for this part of the data, the error are mostly positive down here, right? For this part of data, the error is mostly negative. So in this case, do we have homoscedasticity? Or do we have enough homoscedasticity? That's the question. It's probably not, right? It's pretty obviously a case of heteroscedasticity. Okay? Well, like I said last time, almost every situation we have in reality are heteroscedastic, but if it resembles homoscedasticity enough, then we can make assumption of homoscedasticity. So in this case, it seems that homoscedasticity may not be a very good assumption. Now, let's try to estimate the let's try to run the regression, right? So here what we're doing is we're running the regression of miles per gallon on horsepower using the linear model, and we have this estimate. So we have this result. The horsepower has this coefficient here, and this is our beta hat, and the standard error for this beta hat is 0.0064. Okay, so that's the standard error according to the formula, right? How is this calculated? This is calculated using the asymptotic formula that I introduced before. Okay? All right. But we do not have to calculate the standard error. This is not the only way we can do it. Another way we can do it is by Bootstrap. And the idea here is I'm going to define a function that I'm going to draw, right? What I'm going to draw for Bootstrap here is I'm going to draw many data sets with replacement from my data set. Specifically, I'm going to draw 1,000 data sets. And on each data set, I'm going to run a linear regression. Okay? And this linear regression will give me a beta hat. So each data set, I get a beta hat, beta hat, beta hat, beta hat. In the end, I get 1,000 beta hat. And my standard error for the beta hat is basically the standard error of all the 1,000 beta hat I generate. I calculate their variance, take a square root. That gave me the standard error. So the standard error here for beta hat is 0.0074. Okay, that's my Bootstrap result. Now the Bootstrap result 0.0074 is pretty close to using formula. Formula is 0.0064, right? Asymptotic formula. It's slightly larger. Question: which one is better? Is the Bootstrap estimate better here, or is the asymptotic formula better? Any guess? Which one give you a better standard error here? Well, since I'm talking about Bootstrap, if you're guessing, then you probably should have guessed that Bootstrap is a better answer, right? Which is true. Bootstrap here is a better estimate. The 0.074 is better than 0.0064. And the reason is this standard error. Remember I said last time, in R, whenever you do linear regression in R, the standard error is calculated based on the homoscedastic assumption. Okay? Specifically, we're using this simpler formula. Where is it? Okay? We're using this simple formula, assuming homoscedasticity. Now, the data I just showed you, as we can see that the linear line, right, and the error, it looks like we don't have homoscedasticity. It looks like we are a heteroscedastic situation. So how do we calculate heteroscedastic error? We have to use this formula, right? This is a better formula. So in R, how do we do that? We have to add something, right? So we run the linear regression, but we specify that we want to calculate heteroscedastic error. Okay? So in R, that's how we do it. And then look at the standard error, okay? 0.0074, which is what Bootstrap gave us. So in other words, here if we use the correct formula, asymptotic formula, or if we use Bootstrap, we can both arrive at the standard error. But if we use the incorrect, assuming homoscedasticity, then our standard error is not the best. Right. So there are many situations, as we will see, especially, so this is one illustration, and in the future we'll see many cases in which either homoscedasticity is not satisfied, but more often we just don't even have a formula that we can use to calculate the standard error. Because the linear model is easy, right? The linear model is one of the simplest models. And we can basically have a formula that tells us, according to the central limit theorem, this is the formula for the asymptotic variance. But for more complicated models and methods, oftentimes we do not even have an analytical formula for asymptotic variance, or it's very hard to get. And Bootstrap is always something that you can do. So in the absence of formula for asymptotic variance, Bootstrap always comes to the rescue. Right? So Bootstrap is a very useful tool in estimating the standard errors of the parameter that we want. Okay. All right. What more do I want to talk about in linear models? Well, the linear models do not have to be linear, right? And I'm sure you all know that. One of the most frequently encountered cases of nonlinearity is something like this, where in economics we often have y is something like a growth rate, right? It's a exponential to beta x plus e. We often have a situation like this. That y changes on a multiplicative scale, so that every time, for example, like a GDP growth, right? Then x can be the growth rate, or x can be the time, and the beta can be the growth rate, and then y is the GDP. If we have a relation like that, we can always estimate using linear regression by turning to a linear model, just taking a log, right? Just log y will equal to log a plus beta x plus e, and then we will have a linear model. So that's very often seen, right? So I'm sure you all know this. The other case that's something that's nonlinear, but we can always turn into linear, is elasticity measures, where it's a log model, right? So if we have a model that says log y equal to beta 0 plus beta 1 log x plus e, then this beta 1 essentially is elasticity. And I'm sure you all know that too, right? One interesting thing about doing regression like this is that sometimes you need to be careful if your goal is making predictions. So let me give you an example. I think this kind of regression you're running all the time, which is wage regression. So in wage regression, you have log of wage on the left-hand side, right, typically. And then we have beta 0 plus beta 1, whatever x we're interested in, C, and plus E. And suppose we have our estimate, which is beta 0 hat equal to, let me just say 0, okay? Beta 1 hat equal to, just 1, all right? So I want you to predict this person's wage. What is W hat if I tell you that x equal to 1? What is W hat? To 1? Or is it e to the 1? Or is it what? What is it? Let me change x to 0, okay? So that's probably even easier. If x is 0, what should be y W hat? Okay. Is it correct? Or not? What is it? Any different answers? So I guess the question is, let's still write it a y, right? So if y is equal to this, right? The question is can I, if we have this relationship, can I say ey, okay, given x, is it equal to, right? We know that log y has this relationship. So can I do this? Can I say e to the log y is equal to e to the this, so that e to the log y is just y, right? So it's expectation y given x. Is it equal to beta 0 plus beta 1x? Is it true? The answer is this is incorrect. Okay. So if you have an estimate of beta 0, beta 1, you cannot just use it to plug in here and use it to, exponential. Okay, I forgot to write exponential. exp, right? Beta 0 plus beta 1x. This is incorrect. You cannot have beta 0 plus beta 1 exponential and give you expected y given x. That's the incorrect way to do. But that's a mistake that many people make. Right? They run this regression and they want to use it to estimate y hat, and they just simply y hat is exponential of this. That's wrong. Okay? And the reason why is very simple. You all know what Jensen inequality says, right? So expectation of log y, is it equal to log expectation of y? Obviously, not. Do people know that? Right? It's not equal. So which one is larger? Which one is smaller? Jensen inequality, right? Which is larger? That should be easy. Come on. That's what a log look like, right? If you want. Which one is larger? This one, right? No, that's not. So okay, these two are log. If I take expectation, that's where I am, right? You know, or if I take expectation, I take the log. This is what I am. Okay, so this is basic just inequality. All right. So that's. I hope everybody's clear on this. Okay. So we have this relationship, right? Now, what is log y? The log y, log y is this. Okay. The expected log y relationship is beta 0 plus beta 1 x. Correct. And this is going to be smaller than log of ey. Okay? This is going to be smaller. So in other words, if I guess let's get rid of log, just take exponential here. So the exponential of beta 0 plus beta 1x is going to be smaller than a true ey. Okay? Given x, right? It's going to be smaller than a true ey given x. In other words, you cannot do this to predict ey. That's all y hat, right? Because this is what your y hat should really be. Okay, ey given x. So this is a mistake made by many people. Now, what shall we do, right? What can we do? If this is not equal, how do we predict y hat? Well, it turns out that, again, if you're willing to make a little bit stronger assumption, if you're willing to make the assumption that this E has a normal distribution, again, of 0 sigma squared, then we have a known formula because we know the expectation of exponential of a normal distribution. So in this case, you can write y hat is equal to E y given x, right? That's what it should be, and which is equal to E exponential, okay, beta 0 plus beta 1 x, right? That's your estimation plus 1/2 sigma squared. Okay, that's it. So if you are willing to make this assumption, then your predicted y hat should follow this formula, which is the beta 0 plus beta 1x plus something. This plus something is 1/2 sigma squared. For those people who are familiar with the expression of expected exponential normal, this is essentially what you get. Okay, I love to. All right. So this is a mistake that very commonly made when people do the log model. Okay, And by the way, I call this this type of log linear model, I call it target transform. Target transform, meaning that initially our target variable. Remember in machine learning, the variable that we try to predict is our target, right? So the target is y. So initially, y is our target, and we build a linear model to predict this target. Now, what I'm doing, the log linear model is really transforming the target, okay, transforming from y to log y. That's a kind of transformation. The target transform, so this is a very common case of target transform. As we'll learn later, we'll study many models in which we transform not the target, but the predictor of x, okay? So this is also called featuring in machine learning, so we also say feature transform. So we study many feature transform cases, but this is the case of target transform. Okay. All right. Now we will devote a special lecture to talk about how do we do model selection, etc., etc. But right now, let's just focus on linear model. So if you have a linear model, how do I know whether this linear model describes the data well? Right. Now one thing to do is you can just plot it and to see how well, to visually examine, right? Oftentimes, however, if your x is higher dimensional, if x is many dimensional, it's very hard for you to plot it. Okay, so one way to do is you can instead of plotting x and a y and see if it's a good fit. That's one visual inspection. The other way to do is you plot the y hat on this on the x axis, and you plot the residual on the y axis. You can always do that, right? So we have a model that y equal to beta 0 plus beta 1 x plus e, and once you fit them, okay, So once you fit it, then your y hat is equal to this. So then your residual E is the true y minus y hat, right? So we're going to plot this E hat here, okay, on the y-axis. And I'm going to plot the y hat on the x-axis. So this is the y hat, this is the E hat, and you can see, right? Now, if your linear model is not particularly good, then you will see that E hat has, is not really evenly distributed around 0. Let's take a look at some drawing helps again. So if you're x, if you're y, now if your model is really good, if it's truly linear, then the data should look like something like this, right? Okay. For the truly good model, it should look something like this. In other words, the error, these are the E's, the error should be evenly distributed around each y hat, right? Each value. Is that the case here? No. Okay? Positive here, negative here, positive here. They're not evenly distributed. So this is an indication that your linear model may not really fit the data very well, right? Now later on we will introduce other way to do this, but right now this is one way to look at whether your linear data fits well. So if we change to a quadratic, we're using the same automobile data. So if we change to a quadratic, it looks like it's much better fit, right? Because the error terms are now evenly distributed around 0. And this is another very interesting data set that illustrates our point. It's called Anscombe's quartet, in which we have very interesting 4 different data sets. And these 4 data sets share many, many, many similarities. For example, it's x and a y, okay? The 4 data sets have the same mean x. So the average x is the same for all data sets. They have the same mean for y, okay? They also have the same standard deviation for x. They have the same standard deviation of y. The correlation between x and y is also the same for all 4 data sets. But they look very different. Okay? So now we have 4 constructed data sets. They look almost exactly the same. If you look at summary statistic, they are exactly the same. The mean of x, the mean of y, standard deviation, correlation, everything is the same. But they actually look very different. Now here's the thing. If we run regression, linear regression on these 4 data sets, the result is also exactly the same. So the linear regression fit is the same for all 4 data sets. Okay? So let's run a linear regression, 4 linear regressions. You can see that the coefficients are exactly the same, or almost exactly the same for all 4 data sets. Even R squared is the same. Okay? But obviously, they don't really describe the data very well, right? The linear model. So does this linear model describe the data well? No. Does this one describe the data well? No. This one? No. Only this one describes the data fairly well, right? So how do we see that? How do we discover that? Because these two data sets look almost exactly the same if you look at a summary statistic, and the regression results are exactly the same. So how do you discover that these 3 are not good, but only this one is good? Well, like we said, what you can do is you can plot y hat here, e hat here, and see if e hat is evenly distributed around 0. For this one, is e hat? No. This one? No. This one? No. And this one looks okay. Right. So that's one way of showing that it's a good way to visually inspecting whether your linear model fits the data well. Right? Okay, some other common traps for linear modeling that will make your results less good. So far, when we talk about linear regression, we have been assuming that our data is IID. In fact, in much of our discussion in this course, we are going to assume that our data x, y are IID drawn from the underlying distribution. All right, now that's not the case. So in that case, in economics, we say, for example, cross-sectional data is a typical situation where they're IID drawn. Right? Now we'll discuss panel data, but we're not going to discuss time series, for example, in this course. The feature of time series is that the y values are what? The y values of later time and the y value of earlier time, they are correlated across time. right? So this is a case here. If for people who have, how many people have studied time series? Say, I see, a couple of them, right? You know that this, so here the rho is autocorrelation, and it goes from 0. So the 0 case is really like ID case. It goes from 0 to 0.5 to 0.9, and this is a very highly correlated data. And you can see that obviously, you can see that it follows this kind of trend. So when it's low, it's more likely to be low the next period. If it's high, it's more likely to be high the next period. So this is time series correlation. When we have this autocorrelation in Y, in time series data, you can still do linear regression. Right? Can we still do something like Y equal to, can we still do this? Y equal to beta 0 plus beta 1 x plus e. The answer is you can still do this. And your beta hat will most likely still be the same. Okay? However, what is going to change is your estimate of standard error. Because, let's go back again to the formula. Right? When we derive this formula, we're using the central limit theorem. And when we're using central limit theorem, we're assuming that all the data points are independent. Okay? They're not correlated. But in time series, the y's are correlated, okay? And typically the x's are correlated too. In that case, the standard error formula is no longer correct. And so if you just blindly use the OLS standard error calculation formula, you will end up typically with the inflated significance. So you're more likely to declare that the beta is significant when it's not. So that's why if there's a time series data, we need to use time series model, specifically taking into account of the autocorrelation between the y values. Okay, so we are not doing time series in this course, but this is just caution in detail. And another thing is if you draw y hat here, if you draw e hat here, then it's also heteroscedasticity versus homoscedasticity. It's also pretty clear to see, right? So this is the case of more like a homoscedasticity case, and this is the case of heteroscedasticity. Right? Okay. One particular issue that often plaguing a lot of empirical sort of application analysis is collinearity. So if you have many x, and oftentimes what happens, the x values can be pretty highly correlated among each other, especially if you have several variables that are, you have GDP and then you have GDP per capita or something. Right? So if you have variables that are highly correlated, we have a problem with collinearity. What's wrong with the collinearity? Well, collinearity makes your estimate of a mix of beta hat very unstable, and also their significance level cannot be trusted. All right. So here we let's go to see this. Suppose we have y equal to beta 0 plus beta 1 x plus e. And suppose, the data is like this, and we have this optimal fit. This optimal fit is beta 0 equal to 0, okay, beta hat, plus beta 1, and the beta 1, let's say, is equal to 2, okay? That's beta 1 hat. So that's our estimate for the model, linear model. Now, suppose I have another variable that is highly correlated with this x. Let me make it a little bit more extreme. Let me say I have another variable that's just x, okay, exactly the same x, but I treat it as if it's another variable, and I put it into the model. Okay? So now my model becomes beta 1 x plus beta 2 exactly x, right? So they are highly correlated, obviously. The correlation become 1. Now, what is going to be our estimate of beta 1 beta 2? What is going to be our estimate? Remember, without doing this, the beta 1 hat equal to 2, right? Now, what is beta 1 hat, beta 2 hat? You don't know. The answer is there are numerous combinations which will give you the same fit, right? So we can have 2, 0, 0, 2, 1, 1, 1.5, 0.5, anything. anything as long as they add up to 2, we end up with the same exact fit as before, right? So if this fit is the best before, then here just any combination will give you the same fit. In other words, when the two variables are highly correlated, the estimates become highly unstable. Okay? Extremely unstable. Because it can be here, it can be here, because they are virtually the same variable. And in that case, that makes your beta very untrustworthy. Okay? Now, you can also see this from a formula. This is just one way, the intuitive way of explaining things. So if we go back to the formula, right? Remember this formula? I said, look, the beta j in a linear regression is equal to the covariance of uj and y and the variance of uj. And what is uj is the residual of running the regression of xj on all the other x. Okay? Right? So it's x on the other x and the residual. Now, let's say x1, x2, okay? So for beta 1, using this formula, then we first find out what u1 is. And what is u1? It's running regression of x1 on x2, okay? And find out what the residual. Now, if x2 is highly correlated with x1, meaning that x2 is, explains much of whatever is in x1, what happens to this u? Your u1 is going to be very small, okay? Very small. Because these two are extremely similar. So basically, x2 can explain most of x1. The residual is going to be extremely small. It's going to be close to 0. And what happens when your uj is close to 0? This covariance is a small number, right? This becomes a small number. The variance becomes a very small number. So you have a small number divided by a small number. In the extreme, so suppose the two x are exactly the same, right? We have two exactly the same x. Then u becomes 0. Okay? Now in that case, we have 0 divided by 0. You never know what it is, right? It becomes extremely unstable. Okay? The same story with standard error. The standard error formula for the single beta, if we assume homoscedasticity, this is the formula for variance, but this variance this variance is p times p, right? P plus 1 times p plus 1 matrix. If we look at a single v, then we have this formula, right? This is a single, the variance of a single beta j. And similarly, we have u. We can write it this way: the uj, the variance of u is below, okay, is on the denominator. And if u is small, the variance becomes small. What happens is this variance becomes extremely large. Okay, right? This variance of beta j becomes very large, which makes it insignificant, right? Whatever the value, it's more likely to be insignificant. The p-value is going to be very large. It's going to be insignificant. That's another result of collinearity. Okay. So in summary, collinearity is a problem, right? It makes your beta j, makes your estimate unstable, and also makes the variance inflated. The variance becomes large. The estimate becomes unstable, right? It becomes both unstable and insignificant, right? So what shall we do? And by the way, I just said the case I just described is x. There are two x variables that are highly correlated with each other. Multicollinearity refers to a case in which there may not be any two variables that are highly correlated, but it could be that x is almost completely linearly determined by many other variables, like x2, x3, x4. They could together explain most of x1. That's called multilinearity. And the way to detect multilinearity, collinearity, is to calculate 1 over 1 minus r squared. So we're still running. So, suppose x2 may not be extremely correlated with x1, but together with x3 and x4, okay? Suppose together with x3 and 4, these three variables almost perfectly explain x1. That's multicollinearity. How do we detect that? I run regression of x1 on x2, x3, x3, right? And I look at the r squared. So if they really explain, if the linear combination of these variables almost predict x1, then the r squared is going to be big, right? So 1 minus r squared is going to be small. 1 over this is going to be large. And so whenever this thing is large, I know there may be some trouble with multicollinearity. And this number is called a VIF number. Okay. So what do we do, right? Well, the simplest way to deal with multicollinearity or collinearity is simply to drop variables. If you have many variables and they're highly correlated with each other, you should try to drop some variables so that you don't have this problem, right? That's the simplest way to deal with it. Now, this also explains, one of the things here we also want to say is, when you are dropping variables, you should not drop 2 or 3 at a single time. You should drop 1, take a look at results, drop another 1, take a look at result. You should not drop all of them at a single time. Because why? Because there may be 2 variables that, just in our case, we have 2 exactly the same x, right? Now, they can be both insignificant because they are highly correlated with each other. And so the estimate is unstable, the p-value is very large, so they can both be insignificant, but you should not drop them together, right? Because if you just drop one of them, then this one will become significant, and and its estimate will be stable. Right? So get rid of when you see multicollinearity or collinearity, get rid of variables one by one. Right? So that's the message. Okay. Later on, we also discuss other methodology that deal with at least handle collinearity better than linear model, okay? Better than OLS. We will discuss that later. But when you do OLS, you should pay attention to this multicollinearity issues and indeed try to change your variable or drop some variables so that your model do not suffer from this problem. Okay. All right. Now. So far, what we discuss is OLS, which is least square estimation. And the way that we do least square estimation is we define a loss function, and the loss function is L2. We minimize it. There's an analytical solution. We know that beta hat is equal to x prime x inverse x prime y. Right? So that's how we do things. Now, in doing so, we haven't imposed any assumption on what the distribution of this E looks like. Right? So y is equal to beta 0 plus beta 1 x plus E, but there's no assumption that has been made on E. Okay? And then you can always do linear regression. Now, alternatively, if we're willing to impose a strong assumption on the distribution of E, then we can use maximum likelihood estimation to estimate the value of beta 0 and beta 1. All right? Specifically, remember maximum likelihood estimation is an estimation of distribution, right? Conditional distribution. The distribution of x, y on x. Okay? So using the terminology that we introduced in our foundation lecture, what I want to learn is this py given x. And what I'm going to do is I'm going to propose a model full of many hypotheses that are qy given x. The q is a single hypothesis of what the distribution look like. And then I'm going to choose the best q by minimizing the KR divergence, which is basically maximizing the likelihood, right? Same thing, the log likelihood. All right, so let's try it. We have y, and we have x, and the normal linear model is a model that assumes that. So the normal linear model is our goal is try to learn py given x. What is my model? What is the qy given x? The normal linear model is a model of this, which says that y given x is distributed as a normal distribution. And the normal distribution has this form, right? It's x prime beta sigma squared. Okay? That's our model. So I'm going to assume that y given x has this distribution. This is our q. This is our model. I'm going to use this model to learn the underlying P by minimizing the KR divergence between my hypothesis here and the true underlying P. Again, this is my hypothesis, okay? This is my Q. I'm going to minimize the distance between the two. And minimizing that distance is the equivalent to maximizing the log likelihood, okay? All right. Now I can write this in another form, which is, if y is this normal distribution, then I can basically write y equal to x prime beta, right, plus e, where e is this normal 0 sigma squared, right? They are equivalent. So that's a familiar form that you all have. So once I make this assumption, then I can go ahead and calculate and write down the log likelihood function, right? The log likelihood function is basically this form, where the likelihood is the normal PDF, okay? And you take the log, and you can write it this way, right? Now there are two parameters that I want to estimate. The first parameter is beta. The second parameter is sigma. I also don't know sigma. So the way to do it is I maximize this log likelihood by choosing the sigma and the beta that maximize this. Okay. All right. So let's take a look. Right. If I maximize given sigma, right, given beta, I can take derivative with respect to sigma that give me the best sigma. If given sigma, if I take derivative with respect to beta, that give me the best beta. But if I give you sigma and ask you to take derivative with respect to beta, what do you have? Is beta in this one? No. Is beta in this term? No. Beta is only here, right? So if I choose the beta that maximizes the likelihood, what am I doing? What am I doing? I'm actually minimizing, because this is minus. So choosing the beta to maximize this is equivalent to minimizing this term, right? But is this term very familiar to you? This term is the L2 loss function. It's basically the in-sample error of our OLS regression, right? So in other words, when I choose beta to maximize the log likelihood here, I'm doing exactly the same as what I'm doing when I minimize the in-sample error of OLS of linear regression model. So we end up with the same beta hat. That's the idea, okay? If I take derivative with respect to beta, I end up with exactly the same solution, because the term involving beta is basically the same as the in-sample error term when we are doing OLS regression, okay? OLS linear regression. So they're the same solution. And of course sigma we have additional sigma here, because we assume that it's a normal model. So in other words, maximum likelihood estimation of the normal linear model will give you the same estimate of beta as least square regression, exactly the same. But that's not true for any other kind of model. Okay, that's only true if we are doing the normal linear model. Okay, normal linear model means this: if it's only true when we assume this E is a normal 0 sigma square, then in this case we produce the beta hat that's exactly the same as least square regression. Some coding here, right? If you want to go through the code, the way to do MLE is we need to define the likelihood function, right? So this is what the negative log likelihood function looks like, right? So basically write down the formula, which is this one, right? So basically put down this formula, and you define them. Right? You define this formula, take the log, take the minus, and that's negative log likelihood function. So because we're maximizing the log likelihood function, we're minimizing the negative likelihood function. How do we minimize it? Well, we can use the numerical optimization in R, right? It's a function called optim, and specify some initial point and let R do it for you, right? But what I'm doing here is numerical optimization, because I'm not directly doing the analytical solution, right? Just let numerical methods to find out the best point. And you can see that the solution is basically the same. Okay, it's exactly the same, almost basically the same as the least square solution, with additional estimate. This is an estimate of sigma, right? Specific to maximum likelihood. Okay. All right. Oh, by the way, when I say exactly the same, I mean because the data here is taken from the data here, right? So we did the example, and we did OLS. And you can see that the OLS estimate is exactly almost the same as the maximum likelihood. Okay. All right. Okay. So we talk about using OLS to estimate linear model. We talk about using maximum likelihood to estimate the normal linear model, where we assume the E is a normal distribution. we also talk about the that you can transform your target y into a log form, right? Or you can do log. Now the log form, the log y equal to beta x is actually a nonlinear model, but we're just transforming it into a linear model, right? So that we are estimating using OLS. Now this is not new, or this is not. I hope this is not new to you. So it turns out that linear model can be extended to nonlinear model pretty easily. And that's what I'm going to do next. Okay, we're going to discuss how do we go beyond the linear model while still using OLS. Okay, the one thing is really easy. One way to go beyond the linear model is really easy, which is to do polynomial, right? So here in this data, the model is beta 0 plus beta 1x. It doesn't fit very well, but if I let it do beta 1x plus beta 2x squared all the way to x third, then we have something that fit the data very well. Now, for this model, can I estimate it using, it's a nonlinear model, it's not a linear model. But obviously, this model can be estimated using OLS. And you are all familiar with that, right? I hope, okay? So you'll see that. Because in order to use OLS estimator, we don't need the model to be linear in x. All we need is the model to be linear in what? In beta, okay? So as long as the model is linear in beta, then we can do OLS, right? People clear? Yeah, just think about this x squared as like x2. This is x3, and that's a linear model, right? Okay. So this is a very easy way to extend. So indeed, a polynomial regression. This is called a polynomial regression because we have a polynomial model. But polynomial regression is basically the same as a linear regression. We're doing OLS, just replacing x2 with x squared and stuff like that. Okay, higher terms of x. So let's go through some data. I'm going to fit a polynomial model on a wage data set. Okay, that contains the income of the men in Central Atlantic version of the USA from the census data. So what I'm doing is there's a linear model regression of wage on age. Okay, we're going to do a regression of wage on age, and a simple linear regression probably wouldn't be too good. So what I'm doing here is a degree 4 polynomial. Okay, so all the way to x to the 4th, and basically that corresponds to the coefficients here correspond to beta 0, beta 1, 2, 3, 4 as x to the 4th model. Okay, and the fit looks something like this. So that's easy. Now we can do more. Okay. So far, we have been assuming that our model is global. What do I mean by global? If this is x, this is y. Let's get some data. Okay. So let's have some data. Now, if I fit a linear regression line on a polynomial, this is a linear model. I can also fit a maybe a polynomial model, let's say 4th degree or whatever. Okay. When I do this, so far the model we have been doing are so-called a global model, and by global model I mean we assume the same relationship applies everywhere. Okay. So when I have y equal to gx, right? That's our model. It says that whatever the value of x, y has this relation with x. That's called global. But we don't have to have global models. We can have models that are more local, in the sense that I say when x belongs to, for example, 0 to 100, the relation between y and x is y equal to gx. But if x is belong to 100 to 200, their relationship changes. So it could be y equal to fx, okay? So when x is going to some other interval, it could be y equal to jx. In other words, the relation between y and x does not have to be the same everywhere. That's the idea that we don't have to have a global model. How do we go from global to local? Well, one of the easiest way is to have a so-called piecewise constant regression. It's called a piecewise constant model, which is extremely simple. let's think about again, if I have this data set, what is the simplest? Let's still talk about global model, right? What is the simplest global model we can fit? Simplest one. Is it y equal to beta 0 plus beta 1 x? Is it the simplest model we can fit? That's not a simplest model. I can make it even simpler. Just y equal to beta 0, right? That's the simplest model we ever have, right? And what is going to be this beta 0 hat? Just y bar, right? The average bar. Okay, so that's the simplest model we can imagine, correct? Okay, that's almost not a model, but that's the simplest one can get. And this beta 0 hat, it will be, where is beta 0 hat? Suppose this is our data, right? Actually, let me draw some new, maybe let's do some data here. Okay, so this is our data set. If I use a simple model that y equal to beta 0, that's it, you know x, then what is going to be our fit? What does it look like? It should be something like this line, right? That's basically the y bar, okay? The mean of y. Now, is this model good? No, obviously, it doesn't fit the data at all. So we need to go to a more complicated global model. So we can say, okay, beta 1 plus beta 1 x, that's a more complicated global model, which the fit will be, I don't know, maybe looks something like this. That's still not very good. Still not very good. So let's try a more complicated global model, even more x squared, or maybe let's say, okay, beta 3 x3, then maybe I'm able to get something like this. Okay, that's a global model that looks like it fits the data well. But what I'm going to say is, I don't have to do this. Okay, I don't have to have a global model. I can have a local model, and in each local region, local model means in each region, I'm going to fit a different model. Okay, it's going to have a different relationship y to x. And in the local model, I'm only going to do this extremely simple model. Okay, I'm going to have this simple model in every location, and then and the result will be actually pretty good fit. So what I'm going to do is I'm going to break the x down into many different regions. Okay, I'm going to break x down into all these different regions, and in each region, I'm going to fit this extremely simple constant model. What do I get? In this region, this is going to be my fit, right? In this region, fit, 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 fit. Correct? That's good enough. And together, does it fit the data well? It's pretty good, right? I can make it even better by breaking the x into even smaller regions, right? And then in each region I fit a constant. Then in the end, if we go to extreme, then we basically have this continuous line that give you the fit for the data. So this kind of model is called a piecewise constant. And you can understand why it's called a piecewise, because we're breaking x into many, many different pieces. And in each piece, it's a constant model. Okay? Question. Can I fit the piecewise constant model using the OLS formula? Remember what OLS formula is? Beta hat equal to x inverse. Right? That's our OLS formula. Solution for beta hat. For piecewise constant, it's really easy, because in each region, my optimal beta is basically the y bar in that region, right? But can I also use this formula to directly give me all the different beta? The answer is yes, you can. Because you can turn this local piecewise constant model into basically a linear model. And you can get it. So how do we do it? It's really simple. I'm going to define a bunch of new functions. Let's suppose this is my x variable. I'm going to divide the x into, let me just make it extremely simple, all right? I'm just going to divide the x into two regions. Only two regions, okay? Here we have many, many regions. Here are only two regions. And I'm just going to define two new functions. The first function, let me call it phi1x. And the phi1x is, let this point be alpha, okay? So alpha is this value. Phi1x is I x smaller equal to alpha, and the phi2x is I x larger than alpha. Do people know what this function look like? Each function is a 0, 1, right? So for phi1x, it is 1. It is 1 when x is smaller than alpha. And then it becomes 0, okay? What does this look like to you? It's a 0, 1 function, but there's another name for 0, 1 function, which is, what does this look like to you? It looks like the stairs you climb, right? Okay. So this is called a step function because you're step. Okay, so one step, second step. Okay, all right. So this is also called a step function, and this is what phi1 looks like. What does phi2 look like? The other direction. Phi2 look like this, right? Okay. Phi2 like this. It's 1 when it's larger. So what is our piecewise constant model then? Remember, our piecewise constant model is y equal to beta 1 if, now for this one, right? Y equal to, when x is smaller in this region, we're going to fit a y, right? Fit a constant. And I'm going to call it beta 1. So y equal to beta 1 if x is smaller than alpha, right? And y equal to beta 2 if x is larger than alpha. That is our piecewise constant model for this extremely simple case. Right, everybody gets it? And this beta, what is our estimate? Beta 1 hat is simply equal to y bar in this region, right? In this region, okay? All right. But there's another way to write this, which is y equal to beta 1 times what? Times what? How do I? Times phi1 x, correct? Okay. When x is smaller than alpha, I get beta 1. When x is larger than alpha, this whole thing disappears. Right? Okay. And then what? Plus beta 2 phi2x. Okay. So I can write it this way. And what does this remind you? What does it look like? It's something that is linear in what? Linear in beta. So I can let my big X, I can define my big X as what? As phi1x and a phi2x, right? So I can define this large matrix of big X that basically contains phi1 and phi2, and then I can use this formula, our familiar OLS formula, to directly calculate the beta. Clear? Okay. So use the old OLS formula to help me basically solve for the solution of piecewise constants. Now in piecewise constant, it may not be necessary because piecewise constant is really easy. It's just beta 1 and beta 2. And it's just y bar in every region. But if our model gets more complicated, it turns out that all these piecewise models can all be turned into a linear formulation where we can directly get our beta, including beta 1, beta 2, for using this kind of formula, right? Just because it's linear in beta. And we can do all less. Okay. Right. Okay, so let's try it. Now we go to the same wage data, okay? For this wage data, what I'm going to do now is I'm going to cut it into 4 different regions. To cut it into 4 different regions, we require 3 different cuts, all right? The way to do it automatically in R is I'm going to cut this way. There's a cut, right? Cut this age variable into 4 regions, and the R program will automatically cut into 4 equal percentile regions. And so this is the cut, right? The first cut is 33 years old. Second cut is 49. Third cut is 64 years old. And basically, so we have 4 regions. In each region, I'm going to fit a constant. So in the end, I have 4 different estimates, right? 4 different betas. And that's what it looks like, okay? Actually, there's a cut here, but it's not obvious because the 2 estimates are extremely close to each other. So we have 1, 2, 3, 4, 4 different constants. Okay. So in general, like I said, I can write the piecewise constant model in this form. I can write it as y equal to beta 1 phi 1x plus beta 2 phi 2x, all the way depending on how many regions I have. If I have n regions, then I have beta m phi mx. And then if we define this large phi as the combination of all these phis as a matrix containing all these phis, then I can write this beta hat, our beta hat estimate, will just be this formula or that solution. Okay? Now it turns out that the phi doesn't have to be 0, 1. In piecewise constant model, our phi is a 0, 1 step function. But this phi can be anything. This phi can be any function of x, and we will have this solution, correct? Okay? So in other words, using this phi, using this kind of sort of a way of doing things, we can go from linear model to extremely nonlinear model, because each phi can be a very complicated whatever function you want of x. Right? So what is this way of doing? First of all, what is this phi? We have a name for this kind of phi. This kind of phi is called a basis function. And this type of model is called a linear basis function because it's linear in the basis function. It's not linear in x. It's linear in the basis function. Or you can think about it as a linear in beta. Same thing. So that's why it's called a linear basis function. And the way that we transform, right? So the original linear model is x1, x2, x3, right? We have beta x. Now we're going from beta x to beta phi 1x, phi 2x, phi 3x. Okay? In other words, we're going from x to this phi, right? To this phi x. Okay? And this is called feature transform, okay? Because x is a feature, x is our feature, and we're transforming it into essentially a new feature. That's a machine learning term, feature transform. Right? So after this feature transform, we have this linear basis function model that can be extremely nonlinear, but we can still solve it using OLS. And we can see many different examples in the future. All right? So this linear basis function model is extremely general. We see many demonstrations or similar, instances of this model in this course. So one of the simplest, like I said, the basis function doesn't have to be 0, 1, right? It doesn't have to be a step function. One of the simplest way to go beyond step function is to do a piecewise polynomial regression, right? So previously we were doing piecewise constant, meaning in each region I'm fitting a constant. But in each region I can also fit a polynomial. I can fit a linear, I can fit a polynomial, right? I just do it in each region. That's piecewise, okay? So for example, this is piecewise constant. This will be piecewise linear. This blue line is the underlying true f, okay? You don't see it, but we have this data, all this data. So if we do piecewise linear, it looks something like this, okay? Now, when we go to linear, it turns out that there's something that we desire in addition to simply linear. So take a look at this function here, right? Now, the piecewise constant, maybe it's acceptable visually to you that it looks something like this. But the linear one, it doesn't look too good. And part of the reason is we actually want our model to be not breaking up into all these different pieces. It looks pretty bad, right? And also, it's not clear how to go beyond your region, okay? So one thing that we desire in our model, in addition to fitting the data well, we often desire our model to be at least continuous. Okay, don't break up like this. Be continuous, right? So we can make the piecewise linear model continuous very easily. How do we do that? Let's take a look. What is a piecewise linear model? Well, suppose we only have one cut. So we have two regions, one cut. This cut is Kasai, right? Okay, so this is now. What I'm going to do is for x smaller than this Kasai, smaller than fit, I have a linear model, right? For x larger than this Kasai, this cut, I have another linear model, right? So these are two linear models. What I'm going to do now is going to require these two linear models to be the same, continuous, at the border, okay? Which means we must add a constraint. And this constraint is at the border, at this Kasai, the first model is alpha 0, 1, 0 plus alpha 1, 1 times the Kasai, times the value, has to be equal to the second model. The second model at the border, this one goes away, only alpha 2, 0. So we have this relationship, okay? Alpha 1, 0 plus alpha 1, 1 Kasai equal to alpha 2, 0. And this is our additional requirement. So I can solve this, and it will give me something like this, okay? It will give me something that makes everybody continuous. All right. One question is, without imposing this constraint, how many parameters do I estimate? 1, 2, 3, 4. 4 parameters. But if you add one constraint, how many parameters are left? 3, okay? Only 3 to estimate. And it turns out that you can actually write the model like this after the constraint. Basically, we have a beta 0 plus beta 1x plus beta 2 x minus this cut plus. What this means is that this plus function is, again, is a step function that is 0 if x is smaller than Kasai, and it only, so let me write it. It's actually not step, I'm sorry, it's not a step function. It's something like this. X minus Kasai plus this function is basically equal to 0 if x is smaller than Kasai, and then it's equal to x minus Kasai if x is larger. So basically, we have two regions. It's 0 here, and it's linear here. That's what it is. And this model is equivalent to the model here, which I hope it should be pretty obvious to you. Because once you require them to be the same at the border, then essentially, right? Now I'm going to fit a linear model here in this region. But if I require the second linear model to be the same at this middle at the border, then in the end I will have something like this, right? Okay, I'll have something like this. Has to look something like this. But this model can be written as a single linear line, right? Like this, a single linear line plus an adjustment. But this adjustment only happens after this border, and which is exactly what this model does, right? It's a single linear model plus something. This beta 2. This beta 2 is, this beta 2 is the difference between the slope here and the slope here. Okay, right? So that adding the beta 2, but this linear equation only happens after the border, so that we are essentially, after border we turn a little bit. That's what this model really doing. So this model is exactly equivalent to the model here plus the constraint. It's very easy to derive. You can try it yourself. And you can see that we have 3 parameters to estimate. Because we have 4, but one more constraint, only 3 left. Right? Okay. So this is the end result. And this is what the function looks like, which is, below this is 0, above this it's a linear line. Okay, right? And the other thing, the other benefit of writing this way is you can immediately see that once we write it this way, essentially this is another linear basis function model. Okay? So the first basis function is constant. The second basis function is just x. The third basis function is this function of x. And again, beta 0, beta 1, beta 2 can be estimated by OLS because it's linear in beta again. Okay? All right. Now, what can we go from here? So we just did linear piecewise constant. We did piecewise linear. The next thing we're going to do we're going to fit a second degree and a third degree polynomial in each region. Okay, but we are running out of time today, so we're going to continue next time. But next time we'll show you how to do the piecewise polynomial model like we're showing here. Okay, so let's finish today and continue next week.